Hello, welcome to lesson number 27. Today's lesson covers the topic entitled Method Validation. So the objectives of this lesson are to talk about how to validate an analytical method. For the purposes of this lesson, I'm going to focus mainly on chromatographic analytical techniques, HPLC and GC. So we'll talk a little bit about system suitability, what constitutes a suitable method, different method types. I'll touch a little bit on how to validate a method when you take into account what phase that method is used to support. Method validation attributes, which are taken directly from the ICH guidelines. I'll briefly touch on those, as well as what steps are involved in validating a method. And once a method is validated, how do you ensure that your system is suitable to support that method? So we talk about system suitability parameters also. So you need to have a suitable method in place. And the important question to ask here is, what does a suitable method mean? So methods can be divided into a qualitative method or a quantitative method. And normally for methods, you can look at them in three separate ways. Identification methods are needed to show that it's specific for the compound being identified. Assay and purity methods would look at the concentration or strength of your API, and the most stringent validation requirements are needed in this case. And finally, physical methods, where you look at the physical characterization of your compound. In all cases, you need to ensure that the method is fit for the intended purpose, and importantly, that it supports the process chemistry. Again, we'll talk a bit about ensuring that your method is validated at the phase appropriate level or the phase appropriate stage, and that it's in line with all regulatory requirements. The analytical package must adequately characterize the molecule, and your method, whatever method you choose, has to be validatable and sufficiently robust over time. So again, just to touch on these different method types, the first one we talked about was identification tests. The purpose is to characterize the molecule with supportive data for the claimed structure. So typical tests that would fall under the identification tests would be things like NMR, FTIR, UV, elemental analysis or composition, mass spec, or sorry, molecular weight, HPLC or GC, where we look for retention time markers for identification, or any wet chemistry techniques. The second one then is the assay and purity tests to determine strength and purity of your compound or your impurity. Typical methods here would be chromatographic techniques like HPLC or GC, also TLC, thin layer chromatography or ion chromatography. Titration assay is another one that's used for assay impurity, but titrations wouldn't be considered appropriate for use for specificity testing. Spectrometric techniques like UV, IR, NMR are also good to determine assay impurity. Also, metal analysis would be another technique used to quantify levels of metals. And finally, physical characteristic tests, the purpose of which is to evaluate the physical properties of your compound. So we can look at things like appearance, particle size using Malvern, the polymorph using TGA or X-ray. I suppose the main thing about deciding what physical tests to use is to think about the end game, or what your compound is going to be used for. So how critical or relevant are solid state tests when you're targeting, for example, a solution dosage form, like an injectable or a tablet. So the polymorph or the crystal form may not be as relevant in that case. So we talk about phase appropriate testing, and this chart just illustrates the different phases involved in developing and validating methods. So we start at the preclinical phase, where your molecule is developed in the fume hood. We move on to phase 2, phase 3, phase 1, phase 2, phase 3, and finally to your marketed product. So the rigor of analytical testing obviously varies across those stages. Obviously, you're liberal at the preclinical end, and you're most stringent at the commercial or the marketed product end. So we also look at the intended purpose of the method, what it's going to be used for. For example, your impurity profile may change across the phase of the molecule development. So at preclinical, you may have more impurities that you'd like to look at. And then with the introduction of your process validation, you may eliminate or introduce additional impurities into the profile. So it's important to look at and reevaluate your method for impurities as the phase progresses from start to finish. So to go into a little bit further detail, phase 1 then, normally you characterize your molecule at phase 1 using FTIR or NMR. you develop your primary methods for purities and impurities, typically HPLC or GC. Now you'd rarely use TLC in this case because you're not, TLC isn't as specific as you'd need it. We'd also look at other compounds or other impurities at phase 1 stage using LOD, loss on drying, KF, or heavy metals. The knowledge of the stability of the material is important at the phase 1 stage. So minimally we should do some forced degradation studies or some stability indicating studies on your method at this point. It's important also to be aware of your mass balance, which is your purity and your impurities. Obviously not all impurities will have the same response factor, but we do assume that they're close to 100% at that point until we develop the method further. In phase 2 then, we do need validated methods to support phase 2 testing. We also would look at, say, residual solvents. We'd need a GC method to support, to quantify levels of residual solvents at phase 2. And finally at phase 3 then, this would require the most rigor when it comes to method validation. You need validated methods for your final product as well as your precursors and some of your key starting materials, your key raw materials, and certainly your intermediates. Also at the commercial stage or at the phase 3 stage, you need validated methods to support the cleaning of the process rigs after manufacturing. So you need full validated methods for either rinse or swab methods to support cleaning. So really the amount of validation and the rigor of validation increases stepwise from the preclinical right through to phase 3 or marketed product. So method validation then, the definition is as follows. Method validation establishes by means of laboratory studies that the performance characteristics of the test method meet the requirements of the intended analytical application. So really it provides an assurance of the reliability during normal use, and it provides documented evidence that the method does what it's intended to do or that it's fit for purpose. So there are 2 guidelines that are used for method validation purposes. Both guidelines are critical to get a good understanding of the content of both of those. They are used in method validation, method development labs. So I would advise that you go through these in your own time. Take a good look through them. They're referenced a lot in industry, and it would be wise to become familiar with them. This is the USP guideline document. It's taken out of the USP Pharmacopoeia, and this one is the ICH guidelines. Again, it's a very important document, and please do read through that. It's got a lot of information in it, and I've taken highlights or bits of this document and presented them in the slides, but it would be wise to go through this at your own time also. So the ICH guidelines and the USP guidelines apply to any analytical procedure, technique or technology used in a regulated laboratory. The USP publishes official test methods, also called compendia methods, that are accepted by the USP as already being validated. The USP also publishes guidelines that should be applied to the validation of test methods not developed by the USP. And the background on the ICH is that it's a combination of guidelines it's a harmonized guideline document which comes from guidelines from the US as well as Europe and Japan. Organizations should have their own procedures to define their guidelines or SOPs. So really the ICH and the USP are guidance documents, but every manufacturing site should develop their own standard operating procedures using these 2 guidelines as a help or starting point. ICH is intended for commercial material also. So when you begin to validate an analytical method, as well as using your ICH and your USP guidelines, you have to look at the following performance attributes. Now, again, as I mentioned previously, I'm just going to use HPLC and GC as a guide or as an example, but these performance attributes need to be applied to any analytical method, whether it be a bioanalytical assay or any other type of assay. So the first one then is specificity. So specificity ensures that we're looking at the right thing. And that it can distinguish between negative controls used in your method. It refers to the ability of the method to measure accurately and specifically the substance of interest in the sample in the presence of matrix components. So it's really the degree of interference from things like your active ingredient in your API powder, your any excipients or impurities that might have been introduced, as well as degradation products. So it's an assurance that you're looking at the right peak. Sensitivity then, we talk about LOD and LOQ, which really determines how low your method can go or how reliable your method is at very low quantities. The detection limit of an individual procedure is the lowest amount of analyte in a sample which can be detected can be detected, but not necessarily quantitative. So that's an important point. Normally signal to noise is determined through, normally LOD is determined through calculation of the signal to noise. And we usually say signal to noise around 3 is acceptable. The quantitation limit of an individual procedure is the lowest amount of analyte in a sample that can be quantitatively determined with suitable precision and accuracy. So that's the main differences between the two, the LOD and the LOQ. And the LOQ is normally determined at a signal to noise of 10. The linearity then is the relationship between response and concentration, and is the ability to test to obtain test results which are directly proportional to the concentration of analyte in the sample. And linearity is normally evaluated by plotting signal versus analyte concentration across a range. Normally we pick 5 concentrations at a minimum as per ICH guidelines, and we apply appropriate statistical methods to ensure linearity, like linear regression, coefficient of variation, as well as intercept and slope is looked at. Accuracy then is how close we are to the true value, or normally we talk about recovery from spiked samples. There's 3 ways to determine accuracy. So normally we look at percent recovery of known amounts of analyte added into a blank matrix. We compare to a reference standard, or we do standard additions of the analyte also. So again, the ICH guidelines will give greater insight into how we would look at accuracy experiments. Precision or variability refers to the agreement among the individual test results when a method is applied repeatedly to the same homogeneous sample. It's really a measure of the degree of repeatability or reproducibility of a method, and normally it's expressed as percentage RSD for a statistically significant number of samples. It's commonly evaluated as 3 separate measurements, normally as a repeatability measurement or a reproducibility measurement, as well as intermediate precision. The range is the span with acceptable linearity, precision and accuracy. The range of an analytical method is the interval between the upper and the lower concentration of the analytical sample, and as per Beer's law response, the concentration curve should be linear at least 5 to 6 points in the range chosen. And finally, system suitability is something we'll talk about further, but we need to look at that when we are validating a method. Analyte stability, normally we look at the stability of the analyte once it's in solution and prior to analysis. So we look at the introduction of degradants or introduction of additional peaks over a period of time, say 24 hours when you're holding your sample on the bench. And finally, robustness is the measure of the capacity of the analytical method to remain unaffected by small but deliberate variations in the procedure. So normally we vary things like temperature of the column by a certain degree, or mobile phase prep. We normally vary the organic ratio slightly, even buffering of the pH, we'd look at things like that. And it's an indication of variability during routine use of your method to make sure that it's unaffected by small changes depending on what analyst is using that method. So I've pulled this table from the ICH guidelines. It breaks down depending on what you're looking for. We talked about identification methods and assay methods. So the list of characteristics on the left hand side, they're listed, and then depending on what type of method you're doing, you either carry out the evaluation or not. So for example, if we look at specificity, you can see that it's only required when we're validating identification methods. Impurity assays, you need sensitivity, and if you're doing an assay, sensitivity may not necessarily be needed. So just take a look through that table. Again, you can find it in the guidance documents here. If you want to print out this document, it's handy to keep a copy and refer back to it. So it's listed here, and it goes through an explanation of that table further in the guidance docs. So we talked about the ICH issuing compendial test methods. We don't necessarily validate these compendial methods, but we are required to verify them for use in our own laboratory. So verification of compendial methods is usually methods that come from the USP or the EP, the European Pharmacopoeias, or other monographs, and minimally the verification that's required usually replicates some of the validation activities that we would carry out. You need to demonstrate that the compendial methods are suitable for your intended purpose on your compound in your laboratory. You would need to draw up and get a protocol pre-approved by quality before you carry out this verification of your compendial method. Example of a method that we would look at and verify in our lab would be something like Carl Fisher or water content. Now, linearity may not necessarily need to be carried out in the laboratory because it would have been carried out as part of the compendial validation, but you would need to verify, say, spike recovery studies and precision studies in your own laboratory to make sure you're getting accurate results. Now, normally verification of compendial methods is really left up to your own judgment, and that judgment is justified within your protocol, which is approved by the Quality Assurance Department. So tests that don't need to be verified that come from compendia will include things like residue on ignition, loss on drying, or heavy metals tests. The steps involved in validating a method, then we'd start with the purpose and scope of the method. So we'd select our method and we would define the sample concentrations that the method is going to be used for. We perform additional development of that analytical method. So we carry out some additional tweaks, or we'd look at the method a little bit closer and make sure it's suitable for our intended purpose. We then develop a validation protocol, and within that protocol we look at all the previous parameters that we talked about, like specificity, linearity, range, accuracy, etc. We define our ranges that we look at. We perform what we call a pre-validation activity, so we make sure that our method is suitable and that it passes the specifications detailed in your protocol before you begin. If not, we adjust our method parameters, and when we're happy to go ahead, we get our protocol approved by QA, and then we perform our full method validation in the laboratory. Once the method validation is approved and completed, we develop a standard operating procedure which details out step by step how we carry out the method, and the package is fully approved then. So our method validation protocol report is approved, written up, our standard operating procedure is approved, and all that forms part of your method validation package for each individual method. So this is a nice little visual. It kind of highlights where the different types of quality where different types of quality steps fit when it comes to methods. And at the bottom of the triangle, the very first thing we need to look at is to make sure that the instrument is suitable for its analytical purpose. And this is where we look at analytical instrument qualification, IQ. Talk about system suitability. I've split it down to look at the different parameters of the different controls that are looked at during each phase of the testing, whether it be instrument, application, or validation of the method, along with running of the analytical method on a daily basis, and what controls are used to ensure that your quality is being controlled at all times. So when we talk about system suitability, what we're looking at is the overall performance of parameters of the different testing. And at the bottom of the triangle, the rating procedure visual kind of highlights where the different types of quality where different types of quality steps fit when it comes to methods. And at the bottom of the triangle, the very first thing we need to look at is to make sure that the instrument is suitable for its analytical purpose. And this is where we look at analytical instrument qualification, IQ, OQ, and PQ. We then look at the analytical method validation to make sure that the method is suitable for the analytical purpose. Following on from that, then we look at the system suitability tests to make sure that the analytical system, which is a combination of your method, your instrument, and all your additional parameters, that when they're combined, the system is working adequately before you begin your analysis. And finally, during analysis or during QC testing, we make sure that the system is working appropriately at the beginning, middle, and end of those analyses. So we call them QC checks that are periodically run throughout your method. So the table on the right hand side, I've split it down to look at the different parameters of the different controls that are looked at during each phase of the testing, whether it be instrument, application, or validation of the method, along with running of the analytical method on a daily basis, and what controls are used to ensure that your quality is being controlled at all times. So when we talk about system suitability, what we're looking at is the overall performance of the system, and that's normally a combination of the instrument that we're using as well as the method that's being used on the instrument at the time of use. I've taken a quote from the USP Chapter 621. No sample analysis is acceptable unless the requirements for system suitability have been met. I don't have access to the USP online, so you may actually be able to look up those chapters perhaps from your own libraries, but that's just an excerpt from it. So really what we mean here is system suitability tests We'll verify the actual suitability each time the method or each time the instrument is used, or every day that the instrument is used, along with the method. The test method is invalid if the requirements of the system suitability is not met. And the system suitability must be maintained over the course of the whole analysis. So we talked about system suit checks at the beginning of a run and also at the end of a run. Some of the system suit parameters, again, taken from the ICH guidelines, would be things like resolution. So we need to look at the resolution between two key peaks at the beginning of a run, say in a chromatographic method. We apply a resolution criteria, for example, greater than or equal to 1.5, and we'd make sure that that system suit criteria is also achieved at the end of our run. Resolved peaks are basic requirements in both qualitative and quantitative analysis. We look at things like tailing factor or asymmetry or peak shape. Chromatographic peak should be of the proper shape, but due to various factors, the shape often deviates throughout a run. And for example, the tailing can increase or decrease at the end of a run. Tailing can be reduced by changing mobile phase pH or end capping of stationary phase. So we'd set an acceptance criteria at the beginning of a run and at the end of the run on tailing factors. Normally we'd make sure it's less than 2. Theoretical plates then is a measure of the efficiency of the HPLC column. The signal to noise we've talked about previously. It's useful to identify noise effects on the quantification of impurities. So if the signal to noise increases over time, that will affect how we quantify low levels of impurities. And finally, we look at retention time markers. It's a measure of the time taken for a solute to pass through the chromatographic column. It's calculated as the time from injection to detection, and we would set retention time markers at the beginning and end also. So how often should system suitability be repeated? So as mentioned, it should be system suit solutions should be injected at the beginning of a run, and they should be injected at the end of a run. System suit should be repeated within the run also. For example, injection precision obtained from standard injections dispersed throughout the run, or we call them bracketing standards. So if your instrument is running for 24 hours constantly, it's running a batch, numerous batches, you should intersperse standards throughout that run, so you can bracket and accept samples within those brackets if your system was to drift over time. So calculation of system suit parameters is normally performed before the start of sample injections to repeat or to reduce the risk of invalidating sample results. And finally, just before I conclude, I just wanted to highlight that it's essential that data generated by any analytical procedure, it's essential that the procedure is fit for its intended purpose at all times during its life cycle. And we must be able to monitor and control the performance of your procedures, normally by investigating out of trend data. We normally implement routine monitoring of these methods. And if necessary, we control changes made to the procedure through change control. That's the end of this lesson. Thank you for listening.